In the end, most of what we do is actually more or less connected. Let's say I have an n by n matrix A here. I can think of this matrix as just a bunch of vectors being put together. So I'm going to have n vectors here, and each of them will have n coordinates. Let's say that I can perform the row operation and reduce it to the identity matrix. So the reduced row echelon form for this guy is the identity matrix. So what that means is the rank of matrix A is going to be the number of non-zero rows of this matrix, which is going to be n. So I have that the rank of this guy is automatically n. And this also means that I can find the inverse of this matrix A. And that's because there is one way that we can find the inverse of a matrix. We can do this by putting matrix A together with the identity matrix I. If I can perform the row operation so that the left-hand side becomes the identity matrix, then the right-hand side will be the inverse of my matrix automatically. However, we see from earlier that I can perform the row operation so that my matrix A becomes the identity matrix. So I can do the same thing with this guy and obtain the inverse of my matrix. So that means I can always find the inverse of my matrix. And because A inverse exists, that also means that the determinant of my matrix is not going to be 0. And this also implies that if I have a system AX equal to B, it will always have a solution, and the system AX equal to 0 will only have the trivial solution, which is when my x is just going to be 0. And this is because if I have AX equal to B, I can simply multiply A inverse on both sides. So I'm going to have A inverse AX equal to A inverse B. So then my x is going to be A inverse times B. So that means I can always find a solution. And if I have AX equal to 0, I can once again multiply A inverse on both sides. I'm going to have that my x is going to be just A inverse times 0, which is the 0 vector. So I only have one solution here. Alternatively, I can use the fact that the rank of my matrix is n, and it would follow from our earlier example. This would be in example 2.1 and example 2.3, that the system AX equal to B will always have a solution, and the system AX equal to 0 will only have one solution. And because if rank of A equal to n, then I can conclude that the rows of A is going to be a basis for R to the n for sure. So from the fact that the rank of my matrix is n, I can conclude this fact. And because they form a basis, they are going to be linearly independent for sure, and they are going to span R to the n for sure. So I have all these guys from the fact that the rank of my matrix is equal to n.